Hi, my name is Peter Andras. I'm professor at Edinburgh University. This is my lecture series about the evolution of complex systems. This is lecture 1, the introduction, and this is part 3 of lecture 1. So previously, in the previous parts of this lecture, I looked at biological evolution and the evolution of the education system as examples of systems that we will be looking at and be interested in during these lectures. The third part, the final part of the introduction, looks at the technological system. So we look at advances in computer programming. So if you consider how computer programming started, this goes back to the 1940s, 50s, so just around the end and shortly after the Second World War, when the first computers came around following the technological development during the war. Now, these early computers were big and were very quite difficult to program. So early programs were really series of zeros and ones, and people had to know how to combine these in order to make the computers do what they wanted. A further step was when punch cards came around. On these you would use keywords or short comments, and then the punch card would punch the right holes in it, so the right representation by zeros and ones corresponding to that comment would be on the card. And then you would need to stack many of these cards together into a punch card holder and feed that into the computer, where each card was taken, zeros, ones read out from the card, and then that would instruct the computer about what to do. So at that time, clearly writing long programs was very difficult. The size of the programs was directly indicated by the size of the stack of punch cards that you needed, and there were very clear limitations on how complex and difficult programs can be written. Of course, even at that time, these relatively simple programs were quite complex and solved quite complex problems. Now, the next step after this early stage, where programming was really very much an art, where very few people knew well enough how to program these computers, then came around the first high-level languages like Fortran and COBOL. So these programming languages really contained keywords, contained programming structures like a for cycle or an if-then-else structure or subroutine. So these are blocks of programs which do certain things in the context of the program. So this came around, and that made it much easier to write program than writing sequences of numbers or remembering the processor level operations. Now, Fortran and COBOL makes it much easier to program compared to the direct machine code-based programming. However, this is still quite difficult, and in particular, it's very difficult to write easy-to-understand program that somebody else can understand what the program does, how it does it, and in particular can find any change that might be needed later when the further version of the program needs to be developed. So this was the late 50s, from late 50s until early 70s, when these a range of these programs emerged. Fortran and COBOL were the first. And then by the late 60s and by 70s and 80s, the next level of programming or next generation of programming languages comes around. These are the structured programming languages like Pascal, Ada, C, Algol, and a few others. Now, the main advantage of these languages was that they made much more clear how the variables and data are managed, put more constraints on this. They introduced clearly the procedures and functions as subunits, made it very clear how the data is passed between these procedures and functions and the other parts of the program. See, they made programs much more structured by implementing these constraints. Now, that made programs much more readable and modifiable by people who were not the authors of these programs. And of course, that meant also that it was possible to build bigger programs because although Fortran and COBOL had been used to build quite large programs, including managing spacecraft and managing large databases, government databases. However, with these new structured programming languages, it became possible to write much larger programs because it was much easier to understand what the program does. It was much easier to make sure that unintended effects are less likely to be there. Because of these constraints that were imposed on how the structured programming languages require the writing of computer programs. Then, from in fact by the late 70s really, but from 80s to 90s, we find the emergence of a range of object-oriented programming languages, such as the C++, Delphi, Eiffel, Smalltalk, and Java. Now, here, the key innovation was that they bring in the concepts of encapsulation and the inheritance. On one side, the encapsulation helps managing the data, imposing further constraints of what data is visible inside and outside of certain parts of the program, while the inheritance allows you to build increasingly complex elements or increasingly adapted components of the program, which are based on other components that have been developed before. So these are how you structure the different classes, where one class is based on a previous class, and incrementally you define the classes that deliver the functions that you need. However, having this structure of inheritance makes it much easier to understand what it's done by the program. It also makes it much easier to adapt or change the program by deriving further classes. The encapsulation, on the other side, helps in keeping the data well managed, avoiding, again, the unintended interactions and impacts on the data and how the program runs. So this level of advanced management of variables and subunits improved very much the reusability and readability of the programs. So now people who have not written the program were much more able to understand what the program does. Of course, you also have that the commenting practice improved, so people would explain more clearly what the various bits of the program do. But the following of these constraints that were introduced with object-oriented programming meant that it was really much easier to add new things onto existing parts of the software, so it was much easier to reuse and adapt for future use. Now, moving further, component-based programming came around by the mid to late 90s, really. MFC, STL, design patterns, design concepts from the 90s. These are essentially libraries of components. And In this context, the programming takes the knowing of the library, knowing which component can do what. And essentially what you need to do, you piece these together, and as a result, you get a software program which delivers function by connecting components which deliver certain component functionalities. So it makes programming much easier because essentially everything is given to you. All that you need is to learn what your components can do and then figure it out how you combine them into a software that delivers service. This again improves further the reusability. Typically, these are often based on object-oriented languages and implementations of the components. Again, it's very easy to read by the non-author because the assumption is that the non-author knows the library, knows the component library, knows what the components do, so they can read and understand what the combination of these delivers. Of course, we can also see this as a kind of dumbing down of programming because you no longer need to come up with new algorithms. All that you need is to have a good knowledge of your component library and then combine these elements into functional software. Now, looking at further concepts which came around perhaps in the last 20 years or so, one is a reflection. So this is the idea that the software can look at itself and can understand what its own state and act on that state. Now, reflection has been implemented since the late 90s in various programming languages. However, in practice, it's quite often it is very limited what you can achieve by reflection. And the next element is self-modification, which kind of closely relates to reflection, is how you change the program in response to understanding of its own state. Now, that's the part which hasn't been really implemented in a kind of robust and reliable manner across a range of programming languages yet. There are many approaches to it. Aspect-oriented programming was around in the early to mid 2000s. There are other hardware-based approaches, for example, neural networks do, when you program them, you do have some level of self-modification embedded in these very, very specific programs. However, in general, we are not yet there where self-modification and reflection in combination would work in a robust and reliable way of maintaining and adapting computer programs. Development frameworks is essentially based on the concept of the component-based programming, Spring, Spark, Wicket, and so on, JSF. These are development frameworks that programmers use. Essentially, these frameworks come with a library, this component library, and knowing that particular library, people build specific programs appropriate for the particular framework. And perhaps last to note is the concept of low coding and no coding. This is really around in the last few years, really starting around 2020. The idea here is that you can develop programs with very, very low coding contribution or almost no coding contribution. So you don't need to be a programming expert to develop these programs. Now, how does it work? Well, essentially, these are development frameworks which provide quite often some kind of graphical interface or some kind of very easy to use symbolic interface where people knowing the domain and using programs developed in that domain can build new applications for themselves and for others by piecing together components where really they need to know only very superficially at the very really at the level of practical implications and impacts what each component do, because even the matching together of the components is done more or less automatically. That's in the no coding. And low coding, perhaps you need to write a little bit of code, perhaps a script, to piece together the components. So again, it continues the component-based paradigm, but it goes really to the limit of that, where the user who creates the program really needs practically very little or no coding experience at all, or coding training at all. Right, so this was a very brief overview of how programming evolved from the 1940s until the 2020s. So, how did we get this? So how did we evolve from punch cards and the binary coding of programs to component-based programs, and in particular the kind of low coding, no coding, and framework-based programming? What are the driving forces behind this evolution? Can you understand that? Yeah. Is this good? So is it good that we moved from the kind of real art of programming, where people who did this had really deep understanding of how to write new algorithms, to something that you may say that it's dumbing down of programming, the no coding, low coding environment, where you don't really need to understand how algorithms work, you just need to piece together components that you have, and even the piecing together is done for you automatically. Of course, it's another aspect is, are we more efficient now than at the beginning? And perhaps the answer to that is yes. If you, at the beginning, you needed a lot of time, a lot of effort to write relatively simple programs by today's standards. Today, you may write very useful applications even if you have no programming training. So. And then, what comes next? Can we say anything about what kind of programming paradigm might come next? I mean, clearly, if you look around, AI is having a huge revolution in the last 10 years or so. Does this impact programming? Clearly, there are some works on doing much more automated programming. Perhaps looking at the description of the problem that needs to be solved and derive automatically the right program. I have to say that so far my understanding is that these efforts are not that successful as they were hoped to be. But clearly, yeah, there are many things ongoing. But can we say what's next? What will really work? Probably not yet. And then, information and communication is clearly very important in programming languages and in the programs. It is about information, processing of that information, communication about it. But can we understand more clearly what's the role of information and communication in the context of evolutionary programming languages? So clearly, what I mentioned earlier is that, for example, how we deal with data, that at the beginning, data is accessible across the whole program and you can make errors. Then comes structured programming languages, restricting data. Then comes object-oriented, which restricts even more. So clearly that's very important, but how can we find some kind of much more principled level of understanding of how information and communication is driving the evolution of programming? So, we have seen three examples: biological evolution, evolution of education systems, and evolution of programming. So what's common here is, how can we describe such complex systems and their evolution? How can we analyze them? And what's the role of information and communication in these systems and their evolution? So these will be really the questions that we are aiming to answer in these lectures. So how to describe complex systems, how to analyze them, how to describe their evolution. And in part, we focus on how can I identify the role of information and communication in the evolution of these systems. So in summary, in the third part, I described the evolution of computer programming. And then very briefly, I highlighted the key questions that we will be addressing through these lectures about the evolution of complex systems. Thank you.